So we're going to start with, does the weight give the moment about the center of mass? So basically, is it valid what we do in that when we're drawing the free body diagram of a rigid body, we replace the weight, we say that the weight force acts at the center of mass of the rigid body. Is that valid or not? For those latecomers, please ask your friends about the announcements I made at the beginning of lecture. And do not come late to class anymore. Okay, so say we have a rigid body, and I have its center of mass C. And I have the rigid body is composed of differential masses dm. If I want to calculate the total weight force acting on the body, the total weight force acting on the body is the integral over the body of what? If on each differential mass I have a small, so I'm going to call that dm, and I'm going to have a small d weight force acting on the body. What is the weight force of the differential mass? So I have a small mass dm and I have gravity g acting along minus Ez. So what is the weight force acting on this differential mass? Exactly. Minus dm g Ez. And if I want to find the total weight force acting on the rigid body, please do not come late to class anymore. No one comes late to class anymore. I have important announcements I make in the beginning. You have to listen to them. Class starts at 10:10, and that's it. Okay. The weight force is the integral over the body of the weights of all the differential masses. So the integral over the body of this g Ez dm. Any questions so far? Okay, that's great. So g and Ez, these are constants, right? So I can take some outside the integral, and that's going to be the integral of g Ez, the integral over the body of dm. And what is this integral equal to? The integral over the body of dm? Yes, exactly, the total mass of the body. So mg Ez. So this is what we usually say, that the weight force acting on a body is the total mass of the body times g Ez. Now, we want to see if we have any resultant moments acting at the center of mass. So what is the moment of the weight force acting at the center of mass? Okay. How do you think I'm going to calculate the moment of the weight force acting at the center of mass? I'm going to integrate over the body the moments of all of the differential masses acting at the center of mass. So then, what's the moment of this dm about C? The moment of this differential mass about the center of mass. The moment of this force, sorry. The moment of the weight of this differential mass about the center of mass C.
W cross R minus RC.
There's close, but something is wrong. What do we need to fix in that equation? Yes. Exactly. You have to be very careful. It's R minus RC crossed with the force, always. And you know cross products are not commutative. So A cross B, is it the same as B cross A? No. Okay, so that's going to be R minus RC. R is the position vector to dm crossed with minus, or the force basically, which is minus dm g Ez. Okay. Very well. I'm going to take all the constants outside, so that's going to be the integral G and EZ are constants. G, EZ, the minus is also a constant, and that's the integral of, oh well, I cannot take EZ outside like that. I'll have to not flip the cross product order. So R minus RC dm cross EZ. Okay, great. This looks better. So what I did is I took EZ outside the cross product, but I did not flip the cross product. So I maintained the equality. And then G is a constant, or minus G is a constant that I took in the front. Okay? Any questions? Does that make sense? Great. Then, questions? What is this integral equal to? This one we've seen before. Feel free to chat with your neighbors. Take a minute. What is this integral equal to? Any ideas? Ideas?
R minus RC times M.
Not quite. So R, be careful. R is a function of M or dm. So R is the position vector from basically the origin to my differential mass, and it depends on dm. So I cannot just take this R outside the integral, right? R depends on the differential mass. You could split the integral though into two, the integral of R minus RC dm. You can say that's the integral of R dm minus the integral of RC dm. Think about it. Continue, think about it. I need an answer, or ideas at least. So that's the integral of R dm minus the integral of RC dm, right? Right? What's the integral of R dm by definition? The total mass times RC, right? And then this integral here, I can take RC outside, and I'll get RC, the integral of dm, which is the total mass, right? So what is this integral equal to then? 0. Very well. Great. So what do we get? We get that if we integrate the moments of all the differential masses, the weights of all the differential masses of the body above the center of mass, the moments of all the differential weights is 0. So then, instead of having a free body diagram where we have all the differential masses and all their weights, we can say that this is equal to the same body with the weight acting at the center of mass. How come? Because this total force is equal to the sum of all these forces, and the moment of this force above the center of mass is 0, the same as the resultant moment of all these differential forces. Do we see that? So then we are justified in our free body diagrams when we draw the weight force to draw it acting at the center of mass, and it's being equal to the total mass of the body times the gravitational force, the gravitational acceleration. Does that make sense? Any questions? Okay. Great. Before we continue, again, please do not be late to class anymore. It's very important to come early because we start class at 10:10 and we say important things at the beginning of class. Do not come late to class. It's your responsibility to be here before 10:10. Okay? I'm guessing no one has classes before this, so you can make good plans and be here before class starts. Okay. Let's go back to a rigid body kinetics, the balance laws. So these balance laws we already introduced last week. We have the balance of linear momentum and the balance of angular momentum, 3 forms, right? But all these A, B, C forms are equivalent. Do we remember that? Yes, of course we do, because we're studying day by day, solving all the problem sets. Good job. Okay. So on Thursday, what we did is we looked at translating rigid bodies that are translating. So their angular momentum hc was 0. And we focused on calculating this side of the equation, the sum of moments. Today what we're going to do is we're going to look at the derivative of the angular momentum. How do we calculate that? And we're going to solve rigid problems where we have to look at both sides of the equation, basically. We don't have any more one side is 0. So now what we want to do is how do we calculate the derivative of the angular momentum? That's our question. How do we calculate h dot c okay. If you read the notes about the parallel axis theorem, then you know that HP can be written as IP omega plus RC minus RP cross MVP. That's the angular momentum about any point P, material point P on the rigid body. Okay? And anyone remembers our expressions for angular momentum about the center of mass? We actually do not have to remember them. We can get those equations HC and HO from this, because this is the most general one about any point P. If I take P to be in particular C, the center of mass, then what do I get? If I take point P to be the center of mass, C, what does this equation become? What do I get for HC? Yes. Sorry. Yes, go ahead. What is it? I see omega, yes, exactly. What about for point O? Go ahead. Cross MVO, but VO is 0, so this term goes away, right? So for HC, here we're going to have RC minus RC, and this term goes to 0. For HO, we're going to have MVO, and VO is 0, so this term goes to 0. In component form, for example, for HC, remember we wrote HC equals IC omega, and I was in matrix form. So the components of IC, for example, are IXX, IXY, IXC, IYY, IYZ, ICC, and it was symmetric. So using components where omega is omega x ex plus omega y ey plus omega z ez, we can write the angular momentum as Ixx omega x plus Ixy plus so Ixx omega x plus Ixy omega y plus Xz omega z. That's gonna be along Ex plus Ixy omega x plus Iyy omega y plus Iyz omega z along Ey plus C Xz omega x plus IC YZ omega y plus ICZZ omega z. Easy. Ooh, that was a long expression. I think we had that before in set, you have this expression in the preamble of set 18. You have at least the matrix multiplication which multiplies to this in the beginning of set 18. Okay? Give you a second to copy it. Any questions so far? Sure? Okay, so this is HC. What I want to do is I want to calculate the derivative. I want to calculate H dot C. Okay, as I'm calculating H dot C, what are the components that are fixed, constant, and what are the components that are changing in time? So for example, the ICXX, ICXY, ICXC, are those constants or are those changing in time, the components of the inertia matrix on the rotational basis? They are constants, exactly, right? Because we said the mass distribution, the inertia is a measure of the mass distribution. And the mass distribution about this rotational basis of the rigid body is the same. It's not going to change as the body moves. So these are constants. What about the omegas, the angular velocities? Are those constant? No, they're not, right? So the omegas are not constant. What about the basis vectors, the rotational basis vectors, Ex, Ey, Ez? They're not constant, right? So once we take our derivatives, we have to be careful. Omegas are not constants, and the basis vectors are not constant. So I'll do this. I CXX omega x dot plus I CXY omega y dot plus I CXZ omega z dot. Okay. Okay, so I took the derivatives of all the omega terms. Now I have to take the derivative of all the basis vectors, ex, ey, ec. So that's going to be plus ez dot. Okay, great. Now, how do we calculate the derivative of the basis vectors? Ex dot, ey dot, and ez dot. We had an expression for those. Maybe you can check your notes. It involved a cross product. How do we calculate the derivative of the basis vectors?
Omega cross, or for ex it's omega cross ex.
Okay, perfect. And for ey it's going to be omega cross ey, and for ec is omega cross ec. So this is omega cross ex, and this is omega cross ey, and this is omega cross ec. So basically this last term here, the second term, this whole line, I can replace by omega cross hc. Do you see that? Because I'll take omega outside and I'll get hc. So I'll get omega cross hc. That's going to be the second line. The first line is what I'm going to call h corrotational. Does anyone remember what the corrotational means? We talked about this corrotational derivative when we were looking at a particle moving with respect to the rigid body. So what was, for example, the corrotational velocity of a particle moving with respect to the rigid body? What did that mean? Corrotational velocity, corrotational acceleration, what did those mean? Yeah. More precisely, it's the derivative or the velocity or the acceleration, meaning the derivative of whatever quantity as seen by an observer fixed to the rigid body. Meaning that we assume it's the derivative assuming that the basis vectors are fixed, which is basically what this is here. We're taking the derivative of h assuming that the basis vectors are fixed. So that's our corrotational derivative. I'm sitting in this frame and I'm looking at how the angular velocity is moving. And if I'm sitting in the corrotational frame, then I don't see the frame changing. So this is to say that all this tongue expression I can rewrite as h dot c plus h corrotational c plus omega cross h. Any questions? There should be questions. I'll give you a few seconds. Think about this. Questions, please. Does the corrotational thing make sense? just the derivative assuming that the basis is fixed. The derivative of hc assuming that the basis is fixed. Okay. Now fortunately, if we are looking at motions where the angular velocity is just along z, so if omega is just along ez, meaning that omega x is equal to 0, omega y is equal to 0, these expressions simplify, right? How does hc simplify? Can anyone do this off for me? How many terms will I have left out of the 9 terms here? If omega x and omega y are 0 and only omega z is non-zero, how many terms I have left? 2. Raise your hand for 2. Raise your hand for 3. I need more hands up. Chat. Yeah, I think 3, right? 3, because those omega y, omega x, omega y, omega x, omega y, omega x terms go away and we're left with 3. So I'm left with IC xz omega z ex plus IC yz omega z ey plus IC zz omega z az. And that's very interesting. We're going to talk about this. Just let's see what HC is, and then I'll talk about this. HC, okay, that is I C x z omega dot z, and I'm going to copy it off because I'll have to calculate the cross product otherwise. The expression is in the preamble. IC minus IC yz omega squared ex. This term comes from the calculating the omega cross ey. So this term comes from omega cross ey, this term comes from omega cross ex, and then omega cross ez is 0 because that's going to be ez cross ez. Okay? So that's our angular momentum. This is actually interesting. So, questions? Do I have a mistake? Oh yes, this should be squared. Thank you. Okay. So this is interesting. If we can, let me add this to the main equation. So now our equation MC is equal to H dot C becomes that MC becomes this, where H dot C is this. So think about this. You could have a motion where the angular velocity is just along EZ, but you still have components of the angular momentum about x and y. So maybe you've experienced this. You've put a big load in the washing machine, maybe like a comforter or something like big that where you cannot distribute the loads evenly. And the washing machine is turning, and because the load is not distributed evenly, the products of inertia are non-zero. So then what do you think will happen to the washing machine as it turns? Not only do you have moments along EZ, but you also have moments along EX and EY. So the washing machine is going to start basically bouncing, and then, have you ever seen that before? Why? Because it is rotating about EZ, so we shouldn't have any of the other moments in the other two directions. But because of the mass imbalance, we do have, because the products of inertia are non-zero. Another way, place where you see this, if you have a car and the wheels are not really aligned with the axle. So if the center of mass of the wheel somehow is not aligned with the axle about which the wheel is rotating, even though this is a fixed axis rotation, the angular velocity is just along EZ, you're going on a straight line, say, the products of inertia are non-zero, so you will feel the ride is not going to be smooth. You're going to have forces in the other and moments in the other directions. Okay, so this is actually a really interesting equation. And most of the problems we're going to solve, the products of inertia are going to be non-zero, but in some they will be, and this can lead to interesting dynamics. Maybe this afternoon when you go home, you can Google the motion of a hula hoop with some mass imbalance. And what they actually see is that because of the mass imbalance, if you push the hoop hard enough, it's gonna at some point jump and then continue its motion. So this equation with the mass imbalance leads to some very interesting dynamics. Any questions? Okay, then let's start solving some problems. I have set 20 and set 21 copies here, so feel free to take yours. And let's start with set 20, problem 1. Okay, let us read this problem together. A uniform 100 kilogram beam, this is going to denote its mass by m. So m is 100 kilograms. Is freely hinged about its upper end A and is initially at rest in the vertical position with theta is equal to 0. So initially at rest with theta is equal to 0. Determine the initial angular acceleration alpha of the beam and the magnitude of the force Fa supported by the pin A due to the application of the force P that has magnitude 300 newtons on the attached cable. So they want the initial angular acceleration of the beam and the magnitude of the force at A. Let's not solve for the initial forces. Let's solve for basically Fa and alpha as a function of theta. So solve, we want alpha and Fa as a function of theta. Okay. Forces are involved. This is a kinetics problem. We're going to have to apply the balance laws. First, we're going to follow our steps. Any suggestions on where we should take our origin to be? The origin needs to be a fixed point. A. Yeah, we can take it at A. We can take it at any point, basically. Let's take our origin to be at A, and let us take some basis. I'm going to take this Cartesian basis, like that. If it's not convenient, then we'll change it. But for now, let's stick to this. Step 1, the center of mass of the bar is easy to find. It's here at the center of the bar, right? Maybe I'll call this point D so that I do not confuse C and D. The center of mass of the bar is at its middle. It's easy to find. So if we had a more complicated shape, we're going to need to do more to find the center of mass, basically. Okay? So this is step 1. I figured out, my origin, my basis. Well, we will see. We will see if we're going to have to do anything else. Actually, I'm thinking maybe we should take a rotational basis on the bar. So maybe we'll do Ex, Ey, and then our fixed basis would be Ex and Ey like this. Why is that? So that if I overlap the two, the co-rotational basis is the rotation of the fixed basis by an angle theta, about positive EZ. Okay? Then I can say that the position vector of the center of mass RC, I can write this as RC or XC. I can write this as L over 2 EX, right? How can I calculate VC and AC? Right. So I can use my VO plus omega cross RC minus RO to calculate that. VO is 0 and omega is some omega along EZ. So that's going to be omega EZ cross RC minus RO is L over 2 EX, which is equal to, what is EZ cross EX? Negative EY. Are you sure? It's just EY. Okay, so that's VC and AC. That's going to be equal same way. Alpha minus omega squared L over 2EX. Questions? Okay, next we need to draw the free body diagram of the bar. Go ahead and draw it. I'll pass by and check. You can chat with your neighbors. Free body diagram of the bar, please. So let's take our system to be the bar. I want the free body diagram of the bar. And you have to be very careful now with rigid bodies. You have to be careful about where the forces are applied. That's important. So the weight, for example, is applied at which point? the center of mass. Okay, cool. So what are the other forces and where are they applied? Why is FA vertical? Is that vertical? Right, but is it vertical? So from statics, when you take away a pin, what reaction forces do you put instead? A normal force? The origin, which is A. So both of them are material points on the bar. Is this force vertical? Where's your free body diagram? No, you cannot. Free body diagram, you have to isolate your system. You cannot draw it on the bar. Is this force vertical? This Fn. Is it supposed to be vertical? Is it supposed to be vertical, this force? Mm-hmm.
I'm not sure about the direction of the reactional forces.
You're good, actually. Okay, so we have the weight force acting in the center of mass vertically down. Weight force is mg times ex. Raise your hand if you agree. Great. Then we have the force, I'll call it P. I have the force P. The force P has given magnitude 300 newtons. I'll call that just scalar P. And it has a certain direction, right? What is the direction of the force, the tension force along the cord? Actually, let's call it tension force. What is its direction? It's along the cord, right? So we need to figure out the direction of T. Let me draw a simpler diagram. I have a triangle. I have point A. I have point D. And I have this force T. And this point, maybe I'll call it E. I want to figure out the direction of this force T, okay? So I'm trying to use geometry here. There's something that I know about this triangle, and this angle here is theta. This triangle AED, there's something I know about it. Can you look at the dimensions and tell me what that is? Yeah, so it's an isosceles triangle, right? these two sides are both equal to 3 meters. So this is 3 meters, this is 3 meters. This is an isosceles triangle, so we have two angles that are equal in this triangle. This angle is equal to what? Pi by 2 minus theta. And then these two angles are equal, right? They are the base angles of an isosceles triangle. So they will be equal to theta over 2 minus pi by 4. Theta over 2 minus pi by 4. Let us see if I add all those. I'll get, no, plus. Yeah. Is that correct? Theta over 2 plus pi by 4, and if I add all of them, I'll get pi by pi. So is that correct, or did I have a mistake? Yes.
Isn't this only a one instance? Because if it's vertical, the first angle is 90 degrees, or it's pi over 2, and the angle on the right is not.
Great question. So throughout the motion, the length of this is 3 meters, right? And the length of this is 3 meters also. So as this side changes, this triangle remains isosceles. So at the beginning, when theta is equal to 0, this angle is pi by 2, and the other two are going to be 45, like pi by 4, pi by 4. Theta is going to be 0. And then as theta increases, this angle decreases and these two will increase. So this is valid for any angle theta.
Oh, is that theta over 2 plus? Okay.
Yeah, theta over 2 plus pi by 4. Okay? So then, let us see. I'm trying again to figure out this force T. I know its magnitude, I need its direction. This angle is 90. This angle is pi by 2 minus theta. This angle. Chat with your neighbor. Please write down the direction of the force T. Take a minute. What is the direction of the force T? Discuss, but I need the direction of the force T. I think now it's become a little bit easier to figure that out. Done? Or a question? Done? Okay. Raise your hand if you're done. Okay, give you one more minute. Okay, so what's my answer? Who can give us an answer? Yes. What is it? Minus cosine?
Yeah.
Small ex?
Yes.
Oh, so you express that force in terms of your rotational basis. Okay, small ax plus this way. Let us check this. So it's the cosine minus cosine pi by 4 plus theta over 2 along minus ex, and then sine along e. Okay, that's okay to me. Do we agree with this? Do we have another expression that's in terms of the fixed basis? Yes.
Kind of the same thing, but the cosine and sine, their signs are switched, and then the pi over 4 is negative.
So that would be minus sine theta over 2 minus pi by 4.
Yes. That's for EY.
EY.
Oh, but I did it in terms of the fixed basis.
Let us see, did anyone get the same answer? So what I would do is I would look at this angle. This angle is equal to pi minus pi by 2 minus theta minus pi by 4 plus theta over 2. So that's equal to pi by 4 minus theta or plus theta minus theta over 2. So plus theta over 2. So that's pi by 4 plus theta over 2. And then t is equal to cosine pi by 4 plus theta over 2 along EY. Cosine pi by 4 plus theta over 2 along EY. Right? Because this t along EY and then along EX, I'll get the minus sign. So I got a slightly different expression. I'm not sure if they're equal. Do we agree with this? Questions? So I got my t. I'm going to copy those up here. And then erase the bottom word. Okay. That's step 1. That's step 2. Okay, my p. We'll see which one will lead. Minus cosine pi by 4 plus theta over 2 ex plus sine pi by 4 which is equal to p cosine pi by 4 plus theta over 2 EY minus sine pi by 4. The previous expression might be okay if I do pi minus alpha. I think I'll get that, so it might be correct. We'll have to do some trigonometry to check. Okay, so free body diagram so far. We have the weight force, the force P, any other forces acting on this bar? Normal force? Is it a normal force? More precisely, what is it? A reaction force at A. and its direction is unknown. Remember from statics, when you remove a roller, you get a normal force. When you remove a pin, you get a reaction force that has x and y components, basically. So I have some reaction force at A that they called Fa, so I'm going to call it Fa. So the reaction force Fa, it has some unknown x and y components. So instead you can draw it as two vectors like that, or as their sum. So Fa is Fax Ex plus Fay Ay. But be very careful, this is not a normal force and this force is not vertical. If the pin constrains motion along x and along y, then the constraint force resulting from removing the pin is going to be both along x and along y. So again, if the pin constrains motion along x and along y, the resulting reaction force when I remove the pin is going to have both x and y components. Okay? Very well. This is my free body diagram. Step 3, I want to apply the balance laws because again, I want to find alpha, the angular acceleration of the body, and then the force at A. So now I'm going to apply the balance laws. Which balance law do you think I'm going to apply to find alpha, for example, or Fa? Maybe try to come up with a strategy. Chat with your neighbors for a minute. Come up or try to come up with a strategy to solve this problem. I want to find alpha and I want to find Fa. So it's actually going to be a differential equation for alpha, an equation of motion, and then Fa. But then how would you solve for alpha first? Which equation, which balance law? If you want to apply the balance of angular momentum, then which form? Okay, anyone would like to share some ideas? Ideas. Yes.
One thing I heard you could do sum of moments about A, and then Fa is not used for that, so you can use that to solve for it.
That's a good idea. Your friend is saying that when I sum the moments about point A, what's the moments of Fa about point A going to be? Zero. So I get rid of two unknowns, and I think this will directly get you an equation of motion for alpha. Let us check. So I'm going to do the balance of angular momentum about the fixed point O or the fixed point A. It's the same point. Ma is equal to H dot A. So A is a fixed point, so I'm using which form? B, right? B, so I don't have to put the other terms. Okay, the sum of moments about A. How do I calculate the sum of moments about A? I have to calculate systematically, right? I have to calculate, well, the Fa do not have any moment about A, the moment of the weight about A, and the moment of the force P about A. How do I calculate the moment of the weight about A? What's the expression of it? Yes, R, what's the position vector? R C minus RA, right? RC minus RA crossed with the weight, plus for the force, tension force, what's the moment of that about point A?
RE minus RA.
Exactly, you're great. Okay, I see a lot of people get stuck on this, but it's systematic. I look at the free body diagram, all the forces, and then the moment of the force is the position vector from the point of application where I'm trying to find the moment about to the force, to the point of application of the force crossed with the force. Very systematic. cross h dot a. H dot a, I'm gonna use this expression. So using the same derivation, instead of c, I can put a, and I'll get this expression here. IA x z omega dot z, which is alpha basically. Alpha, which is omega dot minus I c y z omegas ex plus omega squared, thank you, plus I c y z alpha plus IA plus IA xc omega squared ui plus IA cc alpha. Easy. Okay, just copy the expression. Hopefully I did not do any mistakes. Okay, so we can start with whichever side we want. If I want to work on this side of the equation here, I need to find IA ZZ, IA XC, and IA YZ. What is IA ZZ? You need your tables. The moment of inertia of a bar about its end, the axis is perpendicular to the bar. I have some extra tables if you need some at the front. Okay, so we all have our tables open. What is IAZZ? So the axis is perpendicular to the bar and it's passing by its end. So what is that moment of inertia here? Yes. I have an answer. Do we agree with it? Raise your hand if you do. Okay, raise your hand if you agree with this. Maybe I'll give you one more minute to discuss and then I'll take a vote. Yes, you agree? Okay, great. Let's wait a little bit more. So which shape are we looking at? Do we have a bar in the table? Uniform standard bar, do we have that in the table? And do we have that moment of inertia, or do we need to use the parallel axis theorem? Because that's not about the center of mass. Is it still on the table, or do we need to use the parallel axis theorem? I think it's given, right? It's given, the axis about its end. So do we agree with this? Raise your hand if you do. Great, great. Questions? Questions, this is very important. Questions. Okay, so that's 1 over 3 ml squared. What about the products of inertia? What are those equal to? So from the tables, they tell you that the moments of inertia about the center of mass is 0. They don't say it. It's 0 from symmetry. Remember? IAXC, well, about the center of mass, ICXC is the integral of minus XC dm, where if I look at the bar, whatever, if it's, I look at the center of mass and I'm looking at Z is an axis perpendicular to it. So I have, for example, X or EX EY and EZ perpendicular to the page. Okay, so if I want to calculate this integral, the product of inertia of the bar, for every point with coordinates x, z, I have another point here with the same coordinate z but with minus x. So when I sum these two, what do I get? 0. And if I sum all the points on this side, positive x, all the points on this side, negative x, and corresponding z's, then the products of inertia are going to be 0. And also, I can show this using the parallel axis theorem or using the integral about the end of the bar. Point A, if point A is here, I have my EX, my EY, and my EZ perpendicular to the bar. And I'm integrating minus x z dm over the body, but now x and z are the position vectors or the components of the position vector from A, not from C. If I have a point here on the bar with some coordinate x and some coordinate z, I have so what I need to think about now is on the thickness of the bar. Outside the page, if I have a point with some coordinates x, some coordinates z, and then on the other side I have a point with some coordinates x, same x, another one minus z, so these two are going to cancel out. The product of inertia is going to be 0. So what it is that if you have, if the EZ axis, the plane, the EX, EY plane that is perpendicular to the EZ axis is a plane of symmetry of the body, then the products of inertia about z are going to be equal to 0. So if, and that's not if and only if, that's just if. One of the conditions for which the products of inertia are 0, if the EX, EY plane passing by point A is a plane of symmetry. Okay, that's one way to figure out that the products of inertia about A are 0. Another way is about the center of mass, they are 0. In the tables they're not there, so they're 0. Or from the integral, the definition of the products of inertia, they're 0. And then you can use the parallel axis theorem to find the products of inertia at A. So from the parallel axis theorem, IA xz is equal to IC xc with what? What are the other terms? Minus what? You have those notes, right? You also have them in the last problem set. I think it's problem set 18. What was that term? Yes, problem set 18. What was the equation for the parallel axis theorem of product of inertia? Yes. Yes. Right? What are AX and AZ? They are the components of the vector from C to A. No, from C to A. Double checking. C to A, I think it is. From yes, from C to A. So then for that vector, AX is equal to L over 2. AZ is equal to what? 0. So then this is equal to 0. And this is already 0. I get this to be 0. The same for Y, the AZ term is 0. Okay. Make sure that your neighbor understands this. Take a minute, explain it really well to your neighbor, make sure they understand this. Why the products of inertia are 0 in this problem. What is it?
The parallax isn't AX plus AC.
It has different forms for the products of inertia versus the moments of inertia. Did you?
I missed that.
You did not see my announcement and read the notes on parallaxis theorem. I posted the derivation on ads.
I've not read the derivation.
What is it?
I've not read the derivation.
You have to. Maybe I'll record the derivation video. It's a couple pages. That's it.
I think I saw the derivation without the text, but I haven't looked at the notes that you posted.
Okay. Yeah, that's where this comes from.
And I think there was a video that doesn't
A video that, a video that does the parallaxis theorem derivation, but not using tensors. The notes they have both, with tensors, without tensors, using tensors, without tensors. Questions? Raise your hand if your neighbor understands this really well. Okay. Questions? Questions? Okay. Question?
So what we said earlier was that the products of inertia are non-zero if the mass is unevenly distributed.
Yes.
So if, but here we're saying if the plane is a plane of symmetry. So
Yeah.
both of those things are like, I'm not sure.
Like think of a dish. Think of a washing machine again. So I have a washing machine. It's a cylinder, kind of the body of it. Okay. And if I look at the cylinder and the clothes are like this and they're evenly distributed, then the products of inertia are zero. But say that I have a clump of clothes here at the front point, then my EX, EY, let me take that to be at the center of mass. My EX, EY, and EZ is outside. My EX, EY plane is not an axis of it's not a plane of symmetry because I have this mass here that I do not have throughout the cylinder.
So plane of symmetry with respect to mass distribution,
Yes.
not geometry.
But mass distribution and geometry. But yes, mass distribution. You can think of it that way. Yes, mass distribution. But that's a good question. Yes.
So he brings up a good point. Like if you have an irregular body, but the plane is a plane of symmetry with respect to just the mass, we treat it the same way. Like so, if there's just equal amount of mass on either side,
Yes.
regardless of geometry.
It has to do with the amount of mass and it needs to be distributed the same way. Right? Because the moment of inertia has to do with mass distribution. So if you have this mass here but at a different location up there, then yeah, might not work. You might have that some of the products of inertia are zero, some of not. Which reminds me, I have a great small problem I'll give you. I don't have my laptop. Well, I'll post a small problem. I'll ask Ekaterina to solve it in the discussion tomorrow. That has to do with this. Okay? It's an easier problem with systems of particles and you calculate the products of inertia for those. Okay. Okay, let's go back to our main problem. It's taking some time, but that's great because we're learning a lot. So again, this problem was that the bar is being pulled, it's fixed at the point A and it's being pulled by the cord. We want to find the equation of motion of the bar, the angular acceleration alpha, and then the force at A. We did step 1, all the kinetics. Some people might say that finding the products of inertia, this belongs to this step. So in the future, you might find this in the beginning. Well, IA xc is equal to 0, IA yz is equal to 0. Okay. We will not fight about this. You can solve this whatever you want if I do not indicate otherwise. Free body diagram, balance law, I'm going to erase this part. And then these terms are 0. So on this side of the equation, I'm just left with 1 over 3 ml squared alpha easy. That's the side of the equation. Now that side, RC minus RA cross the weight. RC minus RA, it's L over 2 EX. Crossed with the weight that is equal to mg big EX. Okay, plus RE minus RA. Let's name that distance, whatever, 3 meters EX. Crossed with the, I have an expression for the tension force, and actually the one along the rotational basis is going to be the most useful. P we have in the free body diagram. So here that's going to be easy. That's going to be equal to 3P, and then the EX cross EY component, that's going to be the sine pi by 4 plus theta over 2. Easy. Thank you. Okay. Now this one a little bit more tricky because we're mixing bases, but the way we oriented our bases is that EX is cosine theta EX plus sine theta EY cross mg EX. So what will I get from this? L over 2 sine theta minus EC. Yeah, and I'll, okay, let us see questions first, and then what do we do next to find our equation of motion?
Dot along EZ.
Yes, we're gonna project along EZ, exactly, and we will get the 1 over 3 ml squared theta double dot, alpha is theta double dot, plus L over 2 sine theta plus or minus 3p sine pi by 4 plus theta over 2 is equal to 0. This is our equation of motion. It's a differential equation in theta. Okay. Ordinary differential equation in theta. Okay? Questions? Then if I want to solve for FA, what do I do? I want to find the reaction force at A. Balance of linear momentum. What did you say? I want to find the reaction force at A. What do I do? Yes, exactly. We're going to do the balance of linear momentum. Balance of linear momentum. F is equal to the mass times the acceleration of the center of mass. The sum of all the forces, that's the weight, plus the tension force, plus Fa. And these two we know. The weight we know, the tension force we know. Fa is what we do not know, is equal to m. And AC, do we know AC? This is the expression for AC, and alpha we solved for from the differential equation, and omega we can also, once you solve this differential equation, you get theta as a function of time. So basically you get omega and alpha. So we know AC. Okay, and these we know, so we can solve for FA. FA is basically MAC minus MAC minus the weight minus the tension force. Okay, that's it. That's it for this problem. So we actually did more than the question asked for. The question asked for alpha and FA only initially, but we found differential equations in theta to find alpha and FA at any time, basically, throughout the motion. If I wanted to find FA and alpha initially, then initially, what is theta equal to? 0. What is theta dot equal to? Is it starting from rest? Did they say it's starting from rest? 0. So initially theta dot is omega is 0, and you can find everything initially. Okay? You can just replace this value and find whatever you want initially. Double check. Okay? So now we're going to do a second problem. That's going to be pair work, your quiz. We're going to have plenty of time, an hour. But it is the second problem in this set. It's a little bit more difficult because in this one, the products of inertia are not going to be 0. Your system is going to be, so in the problem you're going to solve, you have a rod like that, and this is turning about a bearing here. Your system is going to be this, the vertical rod plus the horizontal rod. This here is your origin. You see there's an unsymmetry that's going to give products of inertia that are not 0. Oh, before you solve this problem also, actually maybe read it for a minute, then I'll give you my just tips to solve this. Read problem 2 from this set. What I want to talk is about the reaction force at the bearing. Okay. If you do not want other papers, I think this is one. This is one. Okay. Do you just need one? Can I take this? Thank you. Okay, so if we look at problem 2, you look at the bearing here. What kind of support it is? What motions does it allow, and what motion does it not allow? Does it allow any displacement at point O? No. So then what kind of reaction force do I have at O? How many components will it have? All 3 components, x, y, and z, because we do not allow displacements along x or y or z. What about rotation? Does it allow rotation about the z-axis? Yes. So no reaction moment about z. Does it allow rotation about the x or y? No. So are we going to have reaction moments about x and y? Yes. Okay. So go ahead, solve this problem. If you have any questions, let me know. I will go to my office for a second and get more answer papers in case we need them. Okay.